this video for section 14.1, we're going to be setting up and evaluating a double integral to find the area bounded by y equals 1 over the square root of x minus 1, the x-axis, x equals 2, and x equals 5. You can begin by sketching the graph of the region and then determine if the region is vertically or horizontally simple and determine your bounds of integration. Once you set up your double integral, you can go ahead and evaluate it. You can pause the video, try this one on your own, and come back and check your work. Let's begin by sketching the graph. When you sketch the graph of y equals 1 over the quantity of x minus 1, the square root of x minus 1, the x-axis x equals 2 and x equals 5. We can begin by looking at a graph something like this: x equals 2, 3, 4, 5, x equals 5, the x-axis, and the line y equals 1 over the square root of x minus 1. You can plot points, use a graphing calculator, and it's going to look something a little bit like this. So the line x equals 2, the line x equals 4, the x-axis and that line bound this region here. Now this region is vertically simple, so I'm going to draw a vertical rectangle on that region. And when you look at the dimensions of this little rectangle, we think the long change here, that's going to be our dy, and that little change in this direction is our dx. And we want to find our differential area, dA. The area of that representative rectangle is going to be the length times the width. Now if you draw the rectangle in this way, make sure you always write your first longest differential side first, dy dx. That way the order of the integration and bounds of integration are going to be correct. So now that we have decided that it's vertically simple, we need to find the bounds. The bounds can be found by looking at the region in terms of the top and the bottom and the left and the right. To determine the bounds for y, since our inside differential is dy, we want to find the inside bounds looking at the bounds for y. We're going to be looking at the bottom of that rectangle to the top of that rectangle. And since we're looking at the bounds for y, I need a bottom y equals and a top y equals, or a low y equals to a high y equals. On that rectangle, no matter where you slide it left and right, the bottom of that rectangle is always 0. So y equals 0 is your lower bound for your inside integral. The top of that rectangle depends on where you are on this curve here, and that curve is the equation 1 over the square root of x minus 1. So the top y equals that curve, 1 over the square root of x minus 1. Now let's look at our bounds for x. When I look at the bounds for x, I'm looking at the left side to the right side of the shaded region. And I want to know what the left x equals and the right x equals so we can determine our bounds for the outside integral. If you slide this rectangle all the way to the left of the shaded region, that left x is equal to 2. I just realized I made a mistake on my graph, the scale here. The left x is equal to 2, and if you slide that all the way to the right, your right x is equal to 5. I was off a little bit here. Alright, so our bounds, I should have double checked my work here. The bounds were given x equals 2 to x equals 5. So here are our bounds. We can go ahead and set up a double integral that will give us the area of that shaded region. Okay, so we have a double integral, and the order of the differential is going to be dy dx because it is a vertically simple region. The inside bounds are in terms of y. The bottom y equals 0 to the top y equals 1 over the square root of x minus 1. And then your outside bounds are for x. X goes from 2 to 5. Now we have an iterated integral. You've practiced doing these already, so we can work through this one. You want to do the inside integral first. The differential is dy. The antiderivative of dy is y. So here we're going to get the outside is from 2 to 5, and then we've got to figure out the inside. The antiderivative dy is y, And then we're going to evaluate the bounds of that from y equals 0 to y equals 1 over the square root of x minus 1. And then once we simplify that, it's going to be our dx. When you plug in the upper bound, you get the integral from 2 to 5 of 1 over the square root of x minus 2. And when you plug in the lower bound, y equals 0, you get 0. So we end up with this single definite integral. Now you can use substitution here and our graphing calculator to approximate. When you evaluate this definite integral, you get the area is equal to 2. And that would be our final answer. I've omitted the steps in evaluating that, but you can go ahead and practice doing that using U substitution, evaluating, and checking with the calculator. Okay, in this example, we want to sketch the region defined by the bounds of integration and then switch the order. Remember, the outside bounds must be constant. The inside bounds can only have variables of the outside differential. Now, in this case, we're not actually evaluating it, but we want to be able to determine what the region is that's depicted by these bounds of integration, and then switch the order of those. Okay, if we look at the bounds for the inside integral, we get the bounds for x. When you're looking at bounds for x, we're looking at the left side of the region to the right side of the region. So your left x is your lower bound, x is equal to the square root of y. Your right x is the upper bound, x is equal to 2. Now in terms of the outside bounds of integration, that's our d differential y, so it's going to be our bounds for y. And when we're looking at the y, you can go from the bottom of the region to the top of the region. That's going to be our bottom y equals to the top y equals. The bottom y equals is the lower bound 0, and the top y equals is your upper bound 4. So these 4 equations are going to be used to sketch the graph. And since the order of the differentials here was dx dy, this would have been drawn using horizontal rectangles. And then to switch them, we're going to switch the orientation of that representative rectangle. So if we sketch the graph from y equals 0 to y equals 4, 0, 1, 2, 3, 4, x equals 2, and this equation, x equals the square root of y. Well, if you let y equal 4, then x is equal to 2. If y is equal to 1, then x is equal to 1, and you get the graph 0, 0. So this is our graph of x equals square root of y, the graph of x equals 2, y equals 0 is the x-axis, and the line y equals 4. The region that is bounded by those is this region here. You want to double check the bounds to make sure that this region on the left side of the region is x equals square root of y. On the right side of this region is x equals 2. The bottom of this region is y equals 0, and the top of this region is y equals 4. Again, the order of this differential here, dx dy, would have indicated a horizontal representative rectangle. Now, to switch the order, we're going to create a vertical representative rectangle. And from that vertical representative rectangle, determine the bounds of integration. So our bounds for y is going to go from the top to the bottom. Bounds for y is going to go from the bottom of that rectangle bottom y equals to the top of that rectangle, y equals, and then our bounds for x, we're going to look at the x, the left x equals to the right x equals. Now switching the order of differentials doesn't simply mean switching the bounds of integration. You have to make some adjustments in order to get the right equivalent iterated integral. All right, so since this is a vertical rectangle that we're looking at in this case, the order of the differentials is going to be in the order of dy dx. Because that longest side of that rectangle is going in the y direction, so the differential y is going to appear on the inside integral. Now the bottom of this rectangle here, no matter where you slide it left and right, the bottom of that rectangle is always going to be y equals 0. The top of that rectangle is on the curve. Now what does y equal on the curve? Well, if this equation is x equals square root of y, if we solve for y by squaring both sides, we get y is equal to x squared. That is going to be our upper bound for y. If you slide that rectangle all the way to the left, that smallest x over here is going to be 0. And if you slide that all the way to the right, that largest x is going to equal 2. So now these are our new bounds of integration. So we can set up this double integral of the function f of xy. We started off with dx dy, so we switched the order to make it dy dx. The inside bounds are for y, which goes from 0 to x squared. The outside bounds are for x, which go from 0 to 2. Now we're not going to evaluate this definite integral because we're not given the actual function f of xy. Okay, so the key in doing these is to sketch that graph, knowing that if the order of differentials is dx dy, that horizontal rectangles was used in the beginning. So we want to switch it to a vertical rectangle so that the order of the differentials is dy dx.